Okay, let's have a look now at the slightly more complicated parts with bounds. So really important that you've understood the basics from before, because we're going to be using those basic ideas to help us with the more complicated bits now, which is essentially how all of maths works. So let's start with this first example, and then what we're going to look at are a few notes, a few rules for what you need to do depending on the calculation that you're doing. But this first example will really help us to understand why we do all of those different calculations. So first of all, it says that we have a square which has side lengths of 30 centimeters, but those measurements have been rounded in some way, and they've been rounded to the nearest 10 centimeters. And what we want to try and do is find the upper and lower bounds for the perimeter of the shape. So what we're trying to find is actually really important here because it completely determines what calculation we're doing. So are we adding numbers together, subtracting, multiplying, dividing, or maybe we're doing a combination of a few of them? With perimeter, it's nice and simple though. We know that to find the perimeter, you simply add up all the sides. So we are doing addition. That's the first thing to note. And then we don't just want to calculate one thing. It actually asks us to find the upper bound and lower bound for the perimeter. So what is the biggest possible perimeter that it could have been? What's the smallest possible perimeter it could have been based on the rounding that's occurred in the measurements of the side lengths? So really simple way to think about this. If you are trying to find the upper bound and you're adding numbers together, what do you want all of those numbers to be? Do you want them to be as big as possible? Do you want them to be as small as possible? Or maybe it's a combination. Well, of course, if you're trying to find the upper bound and you're just adding numbers together, if you want your answer to be as big as possible, of course you want to add big numbers together. If you add small numbers together, you won't get as big an answer as if you add all big numbers together. So these side lengths that we're adding together, these four side lengths on the square, we want all of them to be as big as possible. So then we just think, right, what is the upper bound of the measurement that's given to us? And it says that the side lengths are 30 centimeters, but they've been rounded to the nearest 10. So the biggest possible number that it could have been, it wouldn't be 31, that would round to 30, but we can go bigger. What about 32, 33, 34? It's actually going to be 35. Now 35 rounded to the nearest 10 would actually round to 40, but remember the way that our error interval was set up before. We do still say that 35 is the upper bound, even though it's everything just below it though. So we're going to take this side length of our square, 35, and we know that there's four of them, so we add all of them together. If you add all of those 35s together, you're going to get 140. And then a very similar idea here with the lower bound for our perimeter. We are, of course, adding numbers still to find our perimeter, but this time we don't want the answer to be as big as possible. We want it to be as small as possible. So just think logically, when you're adding numbers together, how do you get the smallest answer possible? Well, of course, you start with really small numbers. So in other words, we want to start with the lower bound of the lengths each time, and that's 25. Add all of those together, and of course you will get 100 for your lower bound. So what we can say here is we don't know exactly what the perimeter of the square actually is, because we weren't given exact numbers to start with, but we can say the smallest possible perimeter is 100 centimeters, and the biggest possible perimeter that we could have had is 140, and the real perimeter will be somewhere in between those two numbers. So then, you're probably thinking, what about if you're doing other calculations? That was only for addition. What about multiplication? What about subtraction? It's absolutely fine to just memorize this little table that I've got below. But actually, if you just think them through logically, like we did with that first example, they're relatively straightforward. The addition one we already covered. If you want the answer to be as big as possible, you need big numbers. If you want the answer to be as small as possible, you want small numbers. Multiplication works in a similar way. If you want your final answer to be as big as possible and you're multiplying things together, you need to be using big numbers. If you're multiplying big numbers, you'll get a big answer, but if you're multiplying small numbers, you'll get a small answer. So for the lower bound, we want to be using as small numbers as possible. Addition, multiplication are the more straightforward ones. Subtraction and division a little bit trickier. Think carefully on these. If you're subtracting two numbers, how do you get the answer to be as big as possible? Well, what you need to do is start with a really big number and to take something small away from it. Think about that logically. 10 take away something small like 2 gives me 8, which is still relatively close to where I started. But 10 take away a big number. Let's say you do 10 take away 9, you're only on 1 now. It gives you a small answer. So if you're doing subtractions with upper and lower bounds, if you want your final answer to be as big as possible, you need to do a big number, take away a small, and then the inverse. If you want your answer to be as small as possible, you want to start with a small number and take something big away from it. Division works in a similar way. Again, just think it through logically. If we want our final answer to be as big as possible, we're going to start with something really, really big, and then we're going to divide by something really, really small. Because what we want is that small number to go into the big number lots and lots of times. That will give us a big answer. And then again, the inverse is true if you want the lower bound with division. Start with a small number, put a big number going into it, and it won't go into it that many times because it's trying to go into a small number and it's a big number itself. That's the way I like to logically think it through. So let's now have a look at the next question. We're still using the same square as before, so we've still got this 30 centimeters that's been rounded to the nearest 10, but this time we're going to work out the upper and lower bounds of its area. So let's start with the upper bound. And again, we can use the table above, or we just think it through logically. How do you find the area of a square? And this is important. Different shapes have different calculations for doing area, but a square is very simple. Multiply the length by the width. So we're multiplying and we want the answer to be as big as possible. We, of course, need the original two numbers to be as big as possible. So we want the upper bound in this case. So we take the 35, times it by another 35, and you can use a calculator for this. It's going to give you 1,225. Same idea with the lower bound. But this time, when we're finding our area, we want the final answer to be as small as possible. If you're multiplying two things together and you want your answer to be as small as possible, what do you need to do? Well, of course, you need to start with two small numbers. So we want the lower bound of the lengths, which are 25, times it by another 25. And again, absolutely fine to use a calculator here.